Okay, so today is program 2, session 3. So we're doing algebra, and in particular, that would be Olympiad inequalities. So, what are we going to talk about today? Well, firstly, we'll talk about what is an inequality. Secondly, we'll talk about AMGM, power means, and then a few snack problems to go with that. And then finally, we will talk about the rearrangement inequality and some corresponding problems as well. Okay, so firstly, what is an inequality? Well, an inequality is a relation that makes a non-equal comparison between two numbers or other mathematical expressions, according to Wikipedia. So, in this lecture, we will discuss some common techniques for solving inequalities, notably AMGM, power means, and then also rearrangement. Okay. All right. Okay, so firstly on AMGM. So this is the statement of the AMGM inequality. So for the arithmetic mean, you've probably seen it quite often in school and like your standard curriculum syllabus. So you might refer to it as the average, right? When you add up the sum of some numbers and then you divide it by how many numbers there were. So that is seen on the left-hand side of this inequality. And then on the right-hand side, which is smaller than or equal to the left-hand side, that is the geometric mean. So that is when you take the product of all of those non-negative real numbers and then you take it to the nth root, where n is the number of numbers there are that you're taking the product of. And then as we can see, equality holds if and only if all these terms are equal. Okay, another thing that we can do with AMGM is just like an extension of our original inequality. So it's called the weighted AMGM. So this states that if you have your non-negative real numbers, you can also kind of like append some positive weights to them. So if you multiply each xi by its corresponding weight, wi, and then you like add them together, and then you divide it by the sum of the weights, then this inequality is true. And once again, equality holds when all the terms are equal. Okay. And then finally, the last thing we need to know is power means, which states that for any non-negative real numbers, and for any non-zero real numbers, p greater than or equal to q, then we're able to define MP as the pth power mean. So you essentially get this formula, right? And then if you plug in P equals to 1 and Q equals to 0, then you actually get AMGM, right? And then if you plug in like P equals 2, Q equals to 1, then you also get something that works, and so on. As long as P is greater than or equal to Q and it's not equal to 0, then it will work. For here, we've plugged in Q equals to 0 as a special case, because you can't divide by 0, right? So we can't directly plug it in, but it does actually converge to the geometric mean. Okay, so that's like a pretty big content dump, but we're gonna figure out how to use all of this info by doing a couple of problems. Okay, so firstly, let's try proving AMGM for the case where n equals to 2. That is, can we prove that x1 plus x2 divided by 2 is greater than or equal to the square root of x1 times x2? Yeah, so how long should we spend on that? Let's just spend 5 minutes on that problem. Oh my gosh, sorry. Oh, I did not realize that I was muted. Okay. Um, anyways, I will just go for it. Thanks for letting me know. So here we are required to prove this thing, right? So at some point, it's probably ideal if we get rid of the 2 on the denominator and then get rid of the square root, right? So if we multiply both sides by 2, then this is what we get, right? And then if we square both sides, then this is what we get. And now we're able to rearrange and then get this is greater than or equal to 0. And then how can we prove that this is greater than or equal to 0? Do we have any idea? Well, oh, that's okay. Yeah, so the nice thing about this is that this rearranges, well, it factorizes really nicely into a perfect square, right? And the one thing that we know about squares is that they are always going to be positive, right? Because if you have a positive number times itself, then it's going to be positive. If you have a negative number times itself, it's also going to be positive. So because of this is actually, I think, what we call a trivial inequality. Because this is true, then we can kind of like go backwards and then show that the AMG inequality for n equals to 2 is true. Okay, so does that kind of make sense? Do you have any questions? Okay, cool. Yeah, let me know if there's any questions. Okay, so the next one that we will try is number 2. So now we're plugging in some real numbers in, right? So if xyz equals to 27, all of x, y, and z are positive, what is the minimum value of x plus y plus z? And for which values of x, y, and z does this occur? Okay, how about we take like 5 to 10 minutes to try this one. Oh no, good question. X, Y, Z can be the same numbers. Okay, I think we can have a look at it now. Does anyone have any idea as to how to approach this problem? If not, I can go through it. Um, what are we given? Our condition is that x, y, z equals to 27, right? So let's think about what that means for the AMGM inequality. We know that by AMGM, x plus y plus z divided by 3 is greater than or equal to the cube root of x, y, z. So in this case, x, y, z is 27, so the cube root of that must be 3. Then what does that mean? That means that x plus y plus z is greater than or equal to 9, right? We get this by multiplying both sides by 3. So therefore, the minimum value of x plus y plus z that we were asked for is going to be 9. And that's going to be when equality holds, right? And if we think back to the condition for when equality holds, that is when all of the terms are equal. So that would be when x equals to y equals to z, which equals to 3. So that is your solution. Okay. Hopefully that makes sense. Let me know if you have any questions. But yeah. So you can always just like plug in numbers to inequalities to find like a bound for another kind of value. Okay. So let's give question 3 a try then. Let's spend like 10 minutes on this one. Okay, I think we can give this one a go. Okay. I am not gonna remember this. Screen. Fit in. Okay, here we have a couple of positive numbers, and then we have x also being positive. Um, yeah. So we want to show that x plus each one, like, and then multiply together is less than or equal to the thing on the right hand side. Okay, so how can we do this? Well, let's think about this, right? What if we take the nth root of both sides? And this is what we get on the left hand side. And then on the right hand side, this is just what we get. Because it was to the power of n before, and now we're taking it to the nth root. So it gets rid of it. Okay, so now what could we do? Well, we can see that we can rearrange this right hand side into a form that is very much like AMGMable. Like you can group the terms together so that you can get this product on the inside of the invert. So over here, this thing, we have that it equals to x plus r1 plus x plus r2 plus x plus rn divided by n, right? Because all the r1 plus r2 plus rn, all of that is going to correspond to this. And then your x is the same as x plus x n times, right? So essentially, what you have is xn divided by n, which just gives you x. So it's the same thing. So now you've written it out like that. So you can perform AMGM on it, right? So now you have n terms, like 1, 2, all the way to the nth term. Now what you can do is you multiply them together, then you take the nth root, and then this inequality will be true. So when you get to this point, then you can kind of just quote AMGM because like how you apply AMGM is, I think, already pretty explicit at this point. Okay, so any questions? If not, we will move on to the next question. Okay, thanks. All right. Number 4, I think this one's quite a bit harder. Um, yeah, also give 10 minutes to try it out, but yeah, this one's a fair bit harder, so just try things out, see how it goes, but don't worry too much if you can't solve it. Okay, let's try this one out. I think this one's like a fair bit harder than the ones we were doing before. So, I think we also need to determine when equality holds. Okay, so, hmm, let's try to get rid of the stuff on the denominator again, because here we have like a bunch of fractions. So, if we multiply both sides by ABC, then this is what we get. Okay. And then one thing we're gonna note is that a to the power 4 plus b to the power 4 plus c to the power 4 is the same as a to the power 4 plus b to the power 4 divided by 2 plus b to the power 4 plus c to the power 4 divided by 2 plus c to the power 4 plus a to the power 4 divided by 2. Right? Because each one's repeated twice, but we're dividing it by 2. So if we use AMGM on this, right? If we use AMGM on this one, then what do we get? Then we get, a squared b squared, yep, plus b squared c squared plus c squared a squared, right? Because when you perform AMGM, then you take the square root of this, and then that would just give you a squared b squared. Okay. Oh, okay, so we know that this thing is true, right? And then now we can rewrite this one, because this is equal to a squared times b squared plus c squared divided by 2 plus b squared times c squared plus a squared divided by 2 plus c squared times a squared plus b squared divided by 2. And then what do we get if we apply AMGM on this? Hmm. Wow. What we're going to do is let's just kind of ignore this one for now. So let's deal with what's inside the brackets, right? So if we do AMGM on b squared plus c squared divided by 2, then that's going to give us b squared c squared, and we're going to take the square of that. So that will give us bc, right? And then what we can do is we can multiply that by the square root of a squared, which is just a. Wait, no, we shouldn't do that. We save this one. Yep, and then we just consider this, and this is greater than or equal to bc. And then we just multiply it by a squared. And then we do that for the other ones as well. So then we get b squared ca plus c squared ab. And then we are done, because this is just the result that we wanted to prove up here. So if you just divide through by ABC, then you get your original inequality. So that is the result. So this one is like, I think a fair bit harder than the other ones, because you have to apply AMGM twice and you have to figure out when to use it what to use it on. So it's definitely harder. But yeah, a fun question, I think. Let me know if you have any questions. Yeah. Okay. So I think this last question and the snacks is also like a fair bit harder. So in our last couple of minutes, let's just talk about the rearrangement inequality. So the rearrangement inequality. So think about if you have two sequences of real numbers, right? And then order them, we're able to order them differently. And express it as like B1, B2, Bn as like a permutation of x1, x2 all the way to xn. So then this expression E, where you have like each ith term between A and B multiplied, then added, this expression is going to be maximized when A1, A2 to AN, and B1, B2 to BN are sorted in the same way. And they're going to be minimized when these are sorted in the opposite way. So what do we mean by sorting? We mean like in terms of size. So if we have A1 greater than or equal to A2, which is going to be like greater than or equal to AN, so if we had a sequence like this, where your A1 is the biggest and then your AN is the smallest, and you order it like that, then you want your B1 to be ordered such that B1 is also the biggest one, B2 is the second biggest, and then BN is the smallest. So then you would multiply each pair like this and then add them. So just suppose you had like your numbers like 2, 3, 4, and then you had your numbers 3, 4, 5. And then from each one of these, you had to multiply it by another one in here, a unique one, and then find what is going to be the sum the sum of all the products, right? So if you did like 2 times 4 and then 3 times 3 and then 4 times 5, what would you get? You would get 8 plus 9 plus 20, right? And then that's going to be 37. But the way that maximizes it is actually going to be if you multiply the biggest one by the biggest one, the smallest one by the smallest one, and then the middle ones together. So then you would get like 6 plus 12 plus 20. Right. And then that's going to give you, 38. So if we use the rearrangement inequality correctly, then we are always able to find like the largest possible permutation and then like the smallest possible one. Okay, so that's kind of like the premise of how it works. Let me know if you have any questions. Otherwise, I think we can try a problem. Okay, so the first one, we're going to prove that a cubed plus b cubed plus c cubed greater than or equal to a squared b plus b squared c plus c squared a. So I'll give you like 2 minutes for this one. Okay, let's give this one a try. So we want to use the rearrangement inequality to prove this. Believe it's like this. Okay, so now we have three numbers A, B, C. We know one of them is going to be biggest. So without loss of generality, we're going to assume that A is the biggest. So let's just say we don't know how we can order B or C exactly because it's not symmetrical, right? So we do have to figure out our cases. So if we said we ordered it like A, B, C, so B is greater than or equal to C, then we know that A squared, B squared, C squared is also going to have the same order, right? So the left-hand side is going to be the permutation that maximizes the expression because you have A times A squared, B times B squared, C times C squared, and then you add all of that up. And then this is not that, right? So it's ordered differently. So then, like, yeah, your solution won't be the maximal one. So this one has to be the maximum one. And then similarly for if you assume that C is greater than B, you also get the same outcome. So yeah, that concludes our lecture then. Thanks for coming. Bye.